understand momentum, or more precisely, let's understand linear momentum. We have a rotational momentum also, which is called angular momentum. We shall be understanding more about angular momentum when we shall be doing the rotational mechanics. But right now, we are more interested in linear momentum. Generally, when we say momentum, it means we are referring to the linear momentum. Linear momentum is product of mass of the body and velocity of the body. Velocity is a vector quantity, so it means the momentum, it also becomes a vector quantity. It means momentum of a body has both the things. It has magnitude also, it has a direction also. Linear momentum is denoted by P, and this is mass into velocity. So this P stands for linear momentum. M stands for mass, which is a scalar quantity, and this V is velocity. This is vector quantity, so obviously scalar into vector, this also becomes a vector quantity. So this becomes, so momentum is a vector quantity. We know Newton's second law of motion is F is equal to, that is resultant force, is equal to, that is delta P, rate of change of linear momentum, that is delta T is tending towards 0, or this is in terms of calculus, we write it as dP by dt, that is the rate of change of momentum is equal to the resultant force or unbalanced force or net force on that body or on that system. Now if we look over here, suppose Fr or F is the same thing. If we take T over here, when we say F delta T or F dt, so this becomes dP. This product of force and a very short duration, this is called impulse. To be more precise, this is called linear impulse. We can also have an angular impulse also. So linear impulse, this is dP or delta P, this stands for change in momentum of the body. So when we say impulse, impulse is when a huge force acts for a very short duration of time, then the product of this huge force and a very short time, this is impulse. It is something like on a nail, when we hammer a nail, then the huge force acts on the nail, and this is what you call as impulse. In impulse, when you talk about the impulse, there is a huge force which acts only for a short duration of time. So unit of impulse is, unit of force is Newton, dt second. So Newton second is unit of impulse, and you can also say is, that is change of momentum. Change of momentum or momentum, they will have the same units. It is mass into velocity. This is mass into velocity. Mass is kilogram, velocity is meter per second. So obviously there is equality sign. So F dt, that is impulse units. You can either say Newton second, or you can say kilogram meter per second. That's one and the same thing. You might be having personal experience from your childhood when a ball was thrown to you, and to catch the ball, this cricket ball or a heavy ball, you had not simply catched it like this, but you had also taken your hands back also. If not, you might have seen the cricketers also, that is when the ball, this heavy ball is coming with a great velocity, they don't simply stop it like this, they don't catch it like this, but they take their hands along with the ball some time before it comes to rest. Why do they do it? Now if we understand from Newton's second law, that is F is equal to dP by dt. When we say F is equal to dP by dt, so F dt is equal to dP, that is impulse is equal to change of momentum. Let's see why it hurts when we try to stop the ball like this and we don't take our hands back along with the ball. When we try to stop it like this, then it means the ball comes and hits our hand and directly comes to a stop. When it directly comes to a stop over here, it means the dt value, that the time duration is very, very small. Momentum is fixed. Suppose over here, right now, it has a momentum of suppose 100 units. It has a momentum of 100 units. Then it comes over here, stops. So final momentum, it has to be 0. So from 100 units to 0 units, that is a change of momentum. So change of momentum is fixed. Now what we do is, when we try to stop it abruptly, instantly, then this duration of time is very, very small. That is, it comes, just bangs and comes to a stop. So it means the collision time is very, very small. Dt is very small. This is fixed. This has to be 100 units. Initially it was 100, then it is 0. So the change of momentum is 100 units. This dt is very small. So obviously, to make this as 100 units, this is very small. This has to be very massive. So it means the force our hand applies onto it, and the force which it applies onto us, that is Newton's third law of motion, to every action there is equal to opposite reaction. Because of this force, it comes to a stop. But we feel the same force. To every action there is equal and opposite reaction, and action reaction, they are always on two different bodies. Because of this force, it comes to a stop. Because of this force in the opposite direction, we get hurt. Now suppose we are trying to catch the ball and we are taking the hands along with the ball. Then what happens is, during all this time, we are increasing the dt. We are increasing this time. Along all the time, we are just applying a force in this direction onto the ball, and we are gradually retarding it, and it comes to a stop. So during this time, that is dt is more, dp is same, that is 100 units. We have increased this time. So as a result, the force we experience is lesser and we don't get hurt. Whenever there is a collision or explosion, the first thing that should occur to your mind is applying conservation of linear momentum principle. You can learn more about collisions and explosions in the dedicated lecture about collisions itself, where we talk about the conservation of linear momentum, we talk about the coefficient of restitution or coefficient of resilience, what we call. We talk about the oblique collisions, we talk about the elastic collision, inelastic collisions, oblique collisions, head-on collisions. So that is, it's a lecture in itself. And then over there you can understand quite in detail, that is how we apply the conservation of linear momentum principle.